All right, so now we get down to some nitty-gritty. We've seen that this inverse matrix is a magical way to solve systems of linear equations when, like ax equal b, when a is square. Okay, so how will you compute the inverse of a matrix? Right? Now you may know this formula for the 2 by 2 inverse. And there's a proof here that this formula works and that A has an inverse if and only if this quantity AD minus BC is not equal to 0. You may be familiar that this is called the determinant. But we have a formula, and this formula works if and only if AD minus BC is not equal to 0. And there's a proof of this. First of all, you assume that AD minus BC is unequal to 0. Okay, since this is an if and only if, you have to prove it both ways. First, you assume this and prove that A is invertible. Then you assume A is invertible and prove this. So we're going to assume that the determinant is not 0. And then the proof simply amounts to showing that this formula works. If AD minus BC is not 0, and you multiply this matrix by the matrix A, you get the identity. And remember, you have to do it on both sides to verify. So A times this matrix A inverse does give you the identity, and A inverse times the matrix A does give you the identity. On the other hand, if you assume A is invertible, what you essentially find out is that if AD minus BC is equal to 0, then no matter what matrix you multiply this matrix A, B, C, D by, the two rows must be multiples of each other. So let me say that again. If ABCD satisfies AD minus BC is equal to 0, no matter what matrix you multiply it by, it must be true that the two rows are multiples of each other. But in the identity matrix, the two rows cannot be multiples of each other, because if I multiply the first row by something, I can't get a 0. Okay? If I multiply the second row by something, I can't get a 0, unless I multiply by 0, which tanks me anyway. So there's no way, in case that AD is equal to BC or AD minus BC equals 0, there's no way to get any kind of formula for an inverse matrix. Okay? So I went over that quickly because it's not really an essential for what we're doing, but it is a good way to see how things work for 2 by 2 matrices. Okay, so let's get down to a serious example, finding the inverse of a big matrix, of a 5 by 5 matrix. So how are we going to do this? We want to find a matrix B such that A times B is the identity matrix. Okay, we can break that up in this way, that A times, we take A times B. Now B can be thought of as consisting of the column vectors of the matrix B. Okay, so I'm writing B as its first column, second column, third column, fourth column, fifth column. Now the result of AB is the identity matrix. I'm going to break I out into its column. E1 is the first column, E2 is the second column identity, E3 is third column, E4 is the fourth, E5 is the fifth column. Now in our definition of matrix multiplication, when I multiply a matrix by another matrix, the columns of the result are simply the first matrix times the corresponding column of the second matrix. If you go back and look at our definition of matrix multiplication, which I can do right here, go back to my definition here, and you can see that that's what we have here. That to get the product of AB, it's A times each of the columns of B separately. Okay. So each of these columns gives us an equation. A times the first column of B must be the first column of the identity matrix. A times the second column of B must be the second column, and so on down the line. So here we have 5 equations to solve. Okay, that seems like a lot of work. Well, what you'd have to, so it looks like you're solving 5 different equations, so it looks like you have to row reduce 5 different times to get the result. So here's the row reduction that gives you the first equation. Remember, we're trying to find AX equals E1. Right? So that's why E1 is the last vector here. This one is AX equals E2, AX equals E3, AX equals E4, etc., all the way down to AX equals E5. And each one of these equations gives us a different column vector. And these are the column vectors of the inverse matrix. I just put all of these columns together. This is the first column of the inverse, the second column, third column, and so on. So I put these columns together. That gives me my inverse matrix. And then you can verify that A times B is the identity matrix and that B times A is the identity matrix. Okay. Now, the thing is that we've solved 5 systems of equations. We actually use the very same row operations in each case. Why is that? Because we row reduced the coefficient part of the matrix. And the row operations needed to row reduce this coefficient matrix are exactly the same as the row operations needed to reduce this coefficient matrix. Same as this one, same as all of them. Okay, so wouldn't it be nice if instead of row reducing 5 separate times, you just row reduce once? Okay. And that's what actually goes on here. All right, now this theorem looks a little complicated, but it really works out to be something quite simple. So I'm going to work through this statement, and then we'll go down to the examples, and you see what it really means. So to compute the inverse of a non-singular matrix, take any non-singular matrix A. Now A is n by n, right? So I have A is n by n. Here it says create the n by 2n matrix M by placing the n by n identity matrix In to the right of the matrix A. So what's that talking about? That means I take A, then to the right of that, I place the identity matrix. Okay. Then I'm going to have 2n columns and n rows, and this is what he calls the matrix M. Okay. So really, to make this a little more clear, probably should just do something like this. Take this off, and take this off. Okay. It's really just this matrix that has 2n columns. I'll put a dotted line there. So M is this matrix here, and that's the number of rows, and that's the number of columns. Now, if I take the RREF of this, I'm going to get some matrix here. Right. Now, if it turns out that this A reduces to the identity matrix, that will happen if A is non-singular. If A is non-singular, this will reduce to the identity matrix, and then I will become some other matrix, which I'll call N. I'm sorry, which I will call J. Okay, and this is the matrix that he calls N. Okay. So he took M by taking I and tacking A and tacking on the identity matrix, row reduced to get another matrix of the same size. Take the second half of the matrix. This J turns out to be the inverse of A. And the proof is that essentially, when you row reduce this matrix here, you're solving n equations at the same time. It's just as if you take A in the first column and row reduce that, and A in the second column row reduce that, A in the third column row reduce that. The operations on A is the same in each case. So why not just do the same operations once on all of the constant columns at the same time? Okay, that may be a little bit hard to swallow, but when you see an example, I think you can understand. Okay. Now notice this is going to work if A is non-singular. If A is singular, we're not sure what happens, but we'll treat that question later. Okay, so let's do some example. Okay. Let's try to find the inverse of this coefficient matrix. Now, according to what we just said, First, you take this matrix and tack on the identity. Then you row reduce. And then you take the second half. And this matrix turns out to be the inverse. So it's easy enough when it comes down to computing it. And you can do this in Sage. Don't want to do this by hand. So you just need to set this up, do the row reduction, and then take off the second half. That's your inverse. Okay, we'll continue on the next video.